So let's give the exact definition of a function. So yes, definition. Last time didn't give it. So here is the definition. So finally f, a relation that assign x a unique value y that we denote fx. So it's an assignment of one value, one unique value y to each x from the domain of the function. So if you look at this definition, try to apply it and check if it is satisfied for each of those figures. So the usual one, this curve is the semicircle. So we have the unit circle. So we already saw it in the previous example that it is a function, and its equation was y equal square root of 1 minus x2. Okay, this one looks like two pieces. So different. It has different definitions. So we can have have the equation. We see here the y for each x here. It takes the same value, so it's y equal 1. So I can see that here I have my y equal to x equal 1. Okay, 1 for x greater strictly to 1 because 1 is excluded. For each x here, negative less than 1. For each x, I assign only one value, which is minus 1. We are at level minus 1 if x is less than minus 1, less than 1. Okay, it's less than 1. So we see that here. Yes, we have only a function also. Okay, there is an assignment for each x, one unique y. Here at 1, my function is not defined. Great. Now the last one, the fourth one, the fourth function. Yes. So for I check that for any x I assign only one y. Okay, only one y. Those dots are not part of the graph, just to show to describe the limit behavior of our function. So here it seems also, yes, for each x I have a unique assignment. So this one also is a function. But if you look at this one, if I try to take an x here, for example, 2, for example, I see that I can, if I sketch this, if I try to find the corresponding y's, I see that I have one y here, another y at this level. So you see, I found for 2.2 y's, okay, y1, y2 here, and another y1 here. Okay, so this is not function. So is not the graph of a function. The graph of a function, and this is the way that we call. We name this way to checking graphically if the graph can be a function or not. The graph of function is what we call the vertical line test. Okay, so it just says that a curve, a plane curve will be, so plane curve will be a graph of okay, so a plane curve is the graph of a function if and only if if and only if any vertical, no vertical, if and only if no vertical line, okay, intersects, okay, the curve in more than one point. Curve more than once, okay, more than once. Okay, so you can use this rule, okay, practical rule, to check graphically and quickly if your function can be or not a graph of a function. So there is an important remark if you want to add here. When we said that we were interested on function given by a formula, it's not always so. There is the functions like that, what we call piecewise functions. Okay, so piecewise functions are functions also given, so for that assigned for an x a unique y, but the y is given different by different formulas. Okay, an example, a simple example is the absolute value function. Okay, so it's the function that is called, it's valid, takes the value 1, x, so let's erase this one. It takes the value x, exactly x, if x is positive, and minus x if x is negative. And its graph is easy to, you have already know, you must know it before already. So for this part, take 0 0, so it's linear formula, for it's a linear equation. So it's a line. The support of this set of points is a line. We need just 2 points to graph this part. So at 0 we have 0 0, this point, and at 0, and at 1 we have x equal 1, the y will be 1 corresponding, so another point. Then you join the 2 points, so you have your graph for this part, y equal x, but you are restricted to work for x positive only. The other part also, you see it that it's a linear line, so we can graph it also. We can forget at the moment x less the restriction. You can just focus on the formula. So for x equals 0, I know that I have 0 0. For x equal minus 1, and the image will be 1. So I have another part like that. Okay. Normally, y equal minus x continues like that, okay? A line. But I'm restricted to take only the x strictly negative. But at 0 0, I see there, yes, at limit, it's at limit, the point is included. So here is the shape of the absolute value function, okay? So let's erase this part, this dots, so that you are not confused later, okay? Great. Okay. Another example. Okay, so let's take away. Yes, another example. So let's read this one, more complex. Let's say more complex function. Here it is. It is defined as it is by the following formula: 0 if x is less than minus 1, square root of 1 minus x 2 if x is between minus 1 and 1 strictly, and then x if x is greater or equal 1. Again here, so I can graph my function. So let's do it. Yeah, I recognize each part as a standard graph, so it's easy for me to do it manually. So here see there's limits minus 1, 1, that's all. Yes, for x1, my x is less than minus 1, minus 1, here is 0. My function takes 0, so an x here, it's the y of the point, corresponding y is 0. That means the point is here, this one. If you repeat like that, you will get always, so you will describe this part of the points. Okay, okay, so you will have this part. Okay, so we will have this part, okay, up to here, including the minus 1. So let's do it like that. Okay, then for x between minus 1 1, we know it's the half of unit circle. Now we are excluding minus 1 1. That means we will have this something like that. Okay, that's at limit, so we will be close to this point. And since this, so here it seems I will stop here. I am not including for this formula, this part of the formula 1. Okay, now what happens at when x is greater or equal to 1? So I see the formula is the equation of a line, but I need to restrict my line to x greater or equal to 1. For x equal 1, it is included, so the image is 1. So I will have the point 1 1. So here, okay, so here it is the first point. Then the other points greater 2 2, it will be 2. Okay, it's a line, so I can just join the 2 like that, and I have my line. So you see how it is, how is the graph in this case. Okay, so from now on, we will, when you have open circle like that, means you are not including the point. When you have strong point like that, filled point, that means you are including the point. Here one small circle open, here yes, it is included. Okay. Okay, so the last definitions, interesting. Yes, properties you are supposed to know. It's about symmetry and monotony. Why is it important? There's two properties are important if we can have them as we study the function, because it can reduce our work when looking for all the properties of the considered functions. Okay, so we said symmetry. So here is about symmetry. So for symmetry, we will say we have two properties. We say f is an even function, is even if you can check this property, f at minus x is equal to fx. F is odd if you can check f of minus x equal minus fx. Okay, and this holds for any x in the domain of f. So this symbol means for any. Okay, this symbol is means for any x. Okay, now so let's see what looks like a function that is even. Let's interpret these relations. So graphically, what happens? Okay, so look at this, what can happen as a consequence of even function, an even function. So the property says each time you take an x, let's say an x here, okay, the minus x will be the opposite. What about fx? Fx is somewhere, let's say it's here, the level fx, so I have the point x fx that is part of my graph. Minus x fx is here. It's f of minus, okay. So this point has coordinate x fx, okay. For minus x, the even function satisfies f of it's a minus x is fx. So it's at this level, okay? So minus x, f minus x is here. It's at the same level, okay? So if you compare now the position of those 2 points, they are symmetric about the y-axis, okay? So even function has symmetry about y-axis, okay? For an odd function, quickly here, x, y, this time here is an x, here is my fx, okay, x fx, this is my fx. So it's here is my minus fx, the opposite. So what about f of minus x? It is equal to minus the fx. Minus fx will be here, the opposite, minus fx. And it says, so we have my position of the point with coordinate minus x, first axis is minus fx, okay? So if you now comparing geometrically, there is a symmetry. The 2 points are symmetric about the origin, okay? So we have symmetry about the origin, okay? So well-known function, you know, I'm sure you know them. So there is the here an example of an even function, y equal x2 is an even function, okay? Here an example of an odd function is y equal x3, okay? So if you knowing, for example, suppose that I could graph part of the parabola, so I can deduce the other part just by symmetry, by flipping the other part by with respect of the y-axis and get the whole graph. So the study that involves many calculation is reduced to the half domain from 0 to plus infinity, for example. Okay, so this is something interesting on this. Again, also, if you know the monotony also, yes, monotony. What is the monotony? The monotony will help us to in the graphing, so the behavior we will know more information on the behaving of our function. So what is monotony? Let's visualize this on a graph x and y. So if you have something behavior like that of your function, at this, if you look, let's say we are here at this maximum point here. So if you take two values here before this point, okay, if you compare an x1 here with an x2 here, you compare the values taken. Here is fx1 and here is fx2. It is at this level fx2. So clearly you have x1 less than x2 or equal, okay? Or strictly, let's say comparing strictly, fx1 is less than fx2. Okay, so you see that the values fx2 increased compared to fx1 each time, and this is true for any x2 that is moving here along this interval, along this small interval, okay? This small interval, along this small interval, you have then this behavior, your function keeps increasing. So this is each time you can check an inequality like that, then you can say yes, it's f is increasing. So if you can check this one for any x1, x2 in interval, okay, f is increasing. We say as increasing, and mostly we will use this symbol just to do things quickly. Decreasing, for example, if you are here you see that if you compare the two values, okay, if you take an x1 here and x2 here, clearly the fx1 is greater than fx2. Okay, if you can check for x1 less than x2, this time the fx1 is greater or equal to fx2, you can say that f is decreasing function, decreasing, and we can use this on the interval, specific interval. Okay, and you know, yes, like the parabola function. Okay, so this is y equal x2. Okay, so here if you take an x1 here and x2 globally, it is clear you cannot have a comparison, global comparison. But if you restrict yourself to the half interval here, sorry, yes, so if you restrict yourself here to 0 plus infinity, you can make these comparisons. So your function here, f is increasing here and f is decreasing on this interval. Okay, so okay, so that's why we specify the interval where we have this monotony. Okay, increasing on here 0 plus infinity, here on decreasing on minus infinity 0. Okay, some functions like the constant function, what can you say? Y equal, for example, 2. Okay, for any x, if you take two values x1 and x2, you can you have always less or equal and greater. So they are increasing and decreasing at the same time. They are constant functions. Okay, this is f is, we call it constant, is the constant function. So this is what globally you need to know about the introduction on the basic properties for function. Okay, thank you.